Well, good morning and welcome to Nani Notes. Today's topic is going to be the zero and negative exponents. Earlier, we had discussed the laws of exponents. It's the law. And that's chapter 8 in your textbook. If you've got that one with a kayak, that one over there with a kayak, McDougal Littel. Specifically in section 8.3. We have an entire section dedicated to the zero and the negative exponent. And you're going to see that, well, it's largely based on, we can derive this from the quotient of powers. And you'll see how that works in just a little bit. Are you ready? Hey, and we'll do some samples from the textbook. How's that? And no, the numbering is going to look a little funny because I matched the numbering to the samples in the textbook. So if you have this textbook, you're in luck. All right, let's hit it. Ready? Let's go. Okay, the negative exponent. Now, for any non-zero, it's a big deal, base a to the negative n power is 1 over a to the n. There it is in the abstract. Now, we'll look at an example here. Now, actually, well, I guess this is more like a derivation. I've got 5 to the third power divided by 5 to the fifth power. Now, if I were to expand this, you can see what happens here. You can see I can divide out the 5s. I can divide out the 5s. I divide out the 5s. I'm left with 1 in the numerator and 5 squared in the denominator. And that's going to give me, that's going to give me 1 over 25. Now, suppose I do this. Now, if I were to expand this way by the quotient of powers law, well, I also could say that's 5 to the 3 minus 5 power, 5 to the negative 2 power. So check this out. 5 to the third divided by 5 to the fifth is 5 to the negative 2 power. It says so right there by this law. And yet we can see by expansion that it's very clearly 1 over 5 squared. And therefore, we can conclude that the zero or negative exponent, for a negative exponent, I'm just going to take the reciprocal of the, well, that's a funny way to say it. Scratch that. We're just going to just follow the a to the negative n, 1 over a to the positive n. Right. So I know this. And we're going to try a few examples. 10 to the negative 2, well, that's 1/100th. And we actually know that because we saw it when we were using place values in our decimal system. That's on the left side of the decimal, we've got 10 to the 0 power, 10 to the first power, 10 to the second, etc. And on the right, we've got 10 to the negative 1, 10 to the negative 2, etc. That's the hundredths place, 10 to the negative 2. 4 to the negative 1, that's, well, 1 over 4 to the first power. Or as we'd say in Yankee land, we'd say 1/4. Nobody talks like that. All right, how about this bad boy? Be careful. And I say B because B is the base. What is the base? Is it 5B? No, it's just B. I don't see any parentheses there. Please excuse my dear Aunt Sally. So you'll notice the 5 stays put. That stays in the numerator over B to the third power with the restriction that B is not equal to 0. Get used to those restrictions. You'll see that a lot more in algebra too. All right. How about this guy? Now, the k has a negative exponent, so only the k is going to move. Now, I can simplify, I can factor out a 2. So I've got 3 over 2x, k to the fourth. And of course, k and x both are non-zero. Remember, since we're talking about law, what is illegal in math? Division by 0. Undefined. How about this puppy? Well, the 6 is going to stay put. That's not being raised to a power. this k to the negative 4 power, that's 1 over k to the 4th power. And I've got k squared in the denominator. I'm just going to end up with that. Okay, we're going to look at the zero exponent. Then we're going to, in this video, we're going to look at actual textbook questions. Help you out a bit. All right, 0. Now this seems pretty simple for any non-zero. Keep that in mind, non-zero base a to the 0 power is 1. Now if you don't believe me, you could just bust out your calculator and you could say, wait a minute, I'm not believing that. Well, go ahead, pick a number, 23. I'm going to raise it to the 0 power. I'm going to say, where's that key x to the y? Oh, here it is. Let's raise that to the 0 power. And what do you know? I got 1. I'll take another number. I'm going to take negative 17. And I'm going to raise that to the 0 power. And I get 1. I'm going to take 0.357. And I'm going to raise that to the 0 power. I get 1. Can't get any easier than that. So here we go. Let's have an expansion about show why this works. 7 cubed over 7 cubed. Well, if I were to expand that, that's 7 divided by 7 times 7 times 7 over my 777 for all you pilots out there. 7 divided by 7 is 1. I get a bunch of 1s, and I'm left with nothing but 1. I keep on dividing. 7 divided by 7, 1. And I'm left with the whole number 1. Now, if I were to follow it this way, check this out. Using the quotient of powers rule, I've got 7 to the 3 minus 3 power, 7 to the 0 power. Therefore, 7 to the 0 power must equal 1. Now, again, we can't divide by 0, so that's why we must have a non-zero base. Well, let's try that. Hang on. Let's take 0 and let's raise it to the 0 power. 0 to the 0 power. Even your calculator knows it's not a number. Undefined. So, how about this one? Piece of cake. 1. How about this? 1. How about this? 1. But notice here I must state the restriction. I didn't have to state it for 10 and 4 since those numbers are clearly non-zero. Whoa, what's going on here? Well, can we work that out? Well, we can say 3x squared. And again, because I can use I've got k to the 0, which is 1. X to the, I've got a quotient here, 9 minus 7, that's x squared. And I've got 12 divided by 4. The coefficients gives me 3. Now again, for restrictions, since I do have a k to the 0 power and I've got an x in the denominator, I have restrictions that the k and the x cannot be 0. All right, let's go to the textbook. Number 4. Number 4 and 6. Again, these numbers correspond to your textbook. 7 to the negative 3. Well, if I employ my laws of exponents, I know that's 1 over 7 to the 3rd power, or 1 over 343. Small number. Now, this is number 6 in your textbook. I'm not crazy about it because you might miss something here. Notice I'm raising, this is my negative exponent. The negative 2 moves to the denominator, but the negative sign is in the parentheses. That's negative 2 times negative 2 times negative 2 times negative 2. 2 more times. When I do that, an even number of times, the negative sign will disappear. Now, I could factor out the negative 1. Negative 1 times negative 1 is positive 1 times negative 1 is negative 1. Then it's positive, negative, positive. It toggles back and forth. So an even exponent with a negative is going to give me an even number. And 2 to the 6, can we do that in our head? Sure. 1/64. Now, hang on, I think I just put a little something up there. This one's not in your book, but let's suppose it was -5. Now, that's going to be 1 over -2 raised to the 5th power in parentheses. That is going to give me an odd exponent, or that is an odd exponent. That's going to give me a negative number. Notice the difference there. Over here in the orange, I factored out the -1 because remember, -2 can be thought of as -1 times 2. I raise -1 to the 5th power and I get -1. So whatever I'm working on with my odd exponent raised to this, or I've got an odd exponent, yes, I've got a negative base run, that's going to give me a negative number. And since it's 1 over -32, I could just simply write that as -1/32. Okay, a little bonus on that one. Why 8, 9, 10? 8 and 10. -4 to 0? Easy. Now, -9/16. We already know it's a non-zero number, so it's 1. But stay with me on this. I'm going to use my distributive property here. And I'm going to say take -9 to the 0 power and 16 to the 0 power. Well, they'll both give me 1, and 1 divided by 1 is 1. So you see it's consistent. It's consistent there. I could take this extra step, or I could just say -9/16 in itself is a non-zero number. Raised to the 0 power, it's 1. I like where this is headed. Okay. Some goofy ones here. And honestly, this is just bad form. Shame on your teacher if they gave it out. 4/3 to the -3. Let's distribute. And I'm going to distribute that -3 to the 4 and the 3, which of course, using my negative exponents property, becomes 3 cubed over 4 cubed. 27/64. And by the way, when I look at those two numbers, I don't even have to check. Someone might say, can you simplify that? Heck no. You already know you can't, because look, in this form, 3 to the 4th, the numbers 3 and 4 are relatively prime. 4 is not prime, but they are relatively prime. They have no common factors other than 1. Okay. Now, how about this bad boy, 0 to the -2? We already know what's going to happen there, right? Boom, can't be done because it is undefined. You just can't do it. Bad 0. Or, bad base. Okay, we're cooking along here. And we're going to do again, this is a goofy way to write it. Let's do the product of powers here. I'm going to say -6 plus 4 is -2, 1, and that's going to be 1/49. Okay? Now, alternatively, you could have done this. You could have converted 7 to the -6 as 1 over 7 to the 6th, and you still, with your division, you get 7 to the -2 power, which is 1/49. Either way, you're going to get the same thing. How about this? Whoa. I'm going to have to just take a power of powers, and I know that my power of powers rule says this: copy down the base, multiply the exponents. See, that algebra, that integer arithmetic that your teacher was telling you is so important, really is, because that's going to give me 3 to the -4th power. Negative times positive is a -1 over 3 to the 4th. And by the way, we know that's 81 because 3 squared is 9, 9 squared is 81. I guess alternatively, you could have done it this way. And you can see, either way, you get 1/81st. Okay, let's keep this momentum going. Oops, I already gave you the answer, 20. Well, that was super easy. And why would anybody write this? That's just nuts. So again, using my negative exponents, or I could do it this way, -3 minus a -5. Either way, I'm going to end up with 36, meaning 6 squared. Okay, let's keep it going. All right, again, this is getting tedious, but we'll get through this. Now, how about here? My negative exponent property and my distributive property, 4 to the -3 power, g to the -3 power. And of course, I'm going to have restrictions. Over there, x can't be 0. And over here, I'm going to have 1 over 64g cubed, and g can't be 0. Always restrictions. So many restrictions. Are we done yet? Almost. Almost. Negative exponent property, and your restrictions are going to be on your y. How about here? Let's distribute. The 6, the coefficient gets raised to the -3 power. The x to the -2 to the -3 power. And the y to the 3 times -3 power. Now, I simplify, and let's get rid of, and I'm just going to use that negative exponent property. We'll put the 6 down there and the y down there. Now, in this case, both the x and the y can't be 0. And you might say, well, wait a minute, the x is in the numerator. Well, yeah, but you had an x to the -2 over here. So that's where that generated that restriction. X and y can't be 0. Now, where's my alternative? Or I guess alternatively, I could have just done this, which honestly I think I would have done in the first place. And then you can see it's going to become this. Ooh, unnecessarily complicated. Let's skip that. Let's get to let's do a word problem. This has gone on long enough. Now, this is kind of fun. The old grain of salt questions. The mass of grain of salt is 10 to the -4th gram. So if I got 100 grams, I'm going to take the mass of the box, divide by the mass of a grain. That should give me the number of grains. So I've got 10 squared. You all can make that conversion. We know that 100 grams, that's 10 squared grams, divided by 10 to the -4. And let's do our laws of exponents. 10 to the 2 minus a -4. Or I could just say this 10 squared times 10 to the 4th. Either way, I employ my rules. 10 to the 6th power. See, I could have done it that way. That's a lot. What's 10 to the 6th? Million? That's a lot of grains. Oh, same question here. Oops, gave you the answer, but that's okay. Same question, number 51. 10 to the -2, how many in a box containing 10 to the 3 grams? Well, okay, that's the same question. Let's move on to something a little more different. Now, I have no idea what a Wolffia Angusta is, but this is in your textbook. This is question number 52. And it's tiny. It's this little tiny fruit that's about 10 to the -4 grams. So that means it's small. Now, the largest pumpkin ever recorded, it must have been in Alaska, had a mass of about 10 to the 4th. So how many times greater is the mass of the largest pumpkin than that of that little tiny wee thing, the Wolffia Angusta? Well, be careful here because they're talking, first off, they use the word kilo there. So you got to keep track. I like this problem because you get a little bit of extra stuff there. If a pumpkin the largest pumpkin is 10 to the fourth kilograms. You first got to convert it to grams, because 1 kilogram is 1,000 or 10 to the third grams. Therefore, the pumpkin is 10 to the fourth times 10 to the third, right? Hey, you remember that? That's 10 to the 4 plus 3, or 10 to the 7th power. That's how many grams that pumpkin is. Now, if I'm going to say that's 10 to the 7th, I want to say how much bigger is that than that little wee thing, the Wolfia Angusta. I'm going to take that, and I know I'll get some botanists complaining about my pronunciations, but that's what I get for posting on the internet. I'm going to take 10 to the 7th divided by 10 to the negative 4, or another way of saying it, how many times does that little tiny number go into 10 to the 7th? Well, I'm going to use my laws, my quotient of powers, 10 to the 7 minus negative 4, which is going to be 10 to the 11th. Wow, that's how many times bigger. That's enormous. So I guess you'll see numbers like this if you're, well, maybe in science especially, and certainly in astronomy. So we'll get used to working with our exponents. And well, I hope you all got something out of this. And if you're using this textbook, remember these numbers. That's number 52 there. And as always, I want to say thank you for watching 90.